Okay, so welcome back. And today we're going to begin 4.3. Sorry, I usually have it already queued up. So hold on one second. Okay, so 4.3, we're going to start doing minimization problems, and we're going to talk about something called duality. And this is going to be very important. In essence, we're going to be able to transform any minimization problem that's a standard minimization problem into a standard maximization problem by using this concept of duality. So the standard minimum form is going to be similar to the standard maximum form, except for a couple of changes, obviously. The objective function is going to be minimized as opposed to maximized. What's the same is all the variables are non-negative. That's the same as in the maximum form. And then the third one is all the remaining constraints are stated in the form of this, where we have a linear combination of variables, but now we're dealing with y variables instead of x variables because, and you'll see why in a moment, but the main thing is the inequality is now flipped, okay? And of course, where these are all non-negative constants. So we're assuming all the constants are non-negative, all the variables are non-negative when we're looking at standard form. Okay, now there's an interesting connection between the standard maximization and standard minimization problems. And this is that any solution of a standard maximization problem produces the solution of an associated standard minimization problem and vice versa, which means that, hey, if we are given a minimization problem, well, if we can find the associated maximization problem, we can use the techniques that we've already learned to solve that problem, and the maximum value for the objective function for the associated maximization problem will be the maximum value of the objective function for the associated minimization problem. Okay, so that's the key. Okay, and so these associated problems are called the dual of the other. So these are what we refer to finding the dual of the problem. That's what we're talking about. So one advantage of duals is that the standard minimization problems can be solved by, again, using the same method discussed in the previous two sections. So let's look at this. So in this case here, we're asked to minimize, and notice that now we're looking at W instead of Z. So when we look at minimization problems, the objective function is going to be W, and in terms of Y1 and Y2. And then we're going to subject these constraints, and of course Y1 and Y2 are non-negative. And so what we do is we set up the matrix. Okay, now this is something different than what we have discussed already. Okay, so what we do is we take our system of equations with the constraints and the objective function, and we set up a matrix just with these, okay? Okay, so notice that this is the first row, second row, and third row. So all we did was just write these out, and then 8, 16, and 0 for our objective. Now, what I did here is what we call transposed the matrix. So what I did was I took this row and made this column. This row created this column, and this row became this column. And so that's what we call it taking the transpose of a matrix. Okay, that's going to be the first step. And then what we're going to do is we're going to use this to write the associated maximization problem, where now this becomes our Z function, and these become the associated or related constraints. Now, here are the two associated problems. Notice that the feasible area is not the same, the points are not the same, nothing's the same. Okay, yet they will have the same optimum value. And so what we find is when we solve the maximization problem for this one, okay, because the z-score here, or not z-score, but the z equation here is going to be maximized at 48. And it turns out that the associated minimum function for the original problem that we're solving is also 48. Okay? And we also find that it's located at 4,1. Okay, so now let's go and write this dual. Okay, so we're going to find the dual of this linear programming problem. So the first thing we do is we're going to write this as a matrix, okay, using the constraints N, W. And so we write 3, 3, 4, 24 as our first row, 5, 1, 3, 27 as our second row, and then 25, 12, 27, 0 as our third row. And also keep in mind that you want the y1s to be in the same column, the y2s to be in the same column, y3s to be in the same column, and then the constants to be in the same column, just like before. Okay. And so this is what we get for our augmented matrix. Okay, when we do that. So now what we're going to do is we're going to transpose this matrix, and notice that we have a 3 by 4 matrix. And so it's going to turn into, when we transpose it, it's going to turn into a 4 by 3 matrix. And so when we transpose it, we get this matrix here. So make sure you're following along on paper and that you're doing this. So pause the video, make sure you're able to do this and get the same results. Okay, now what happens is these become the constraints of the associated maximization problem, and this becomes our z equation. And so notice how these are all related. Notice also that the inequalities get flipped. Okay, in the original setup, they're all greater than or equal to, right, for the minimization problem. When we change it to a maximization problem, they become less than or equal to. Okay, so now we've got our system. Now we can go ahead and set up our initial tableau. Okay. And then once we set up our initial tableau, just like we did before, then we can go ahead and use the simplex method to solve that tableau, okay, to solve that problem. Okay, so notice the duality here. Given problem, we'll have m variables and n constraints. The dual problem will have n variables and m constraints. In the given problem, the coefficients from the objective function, okay, so we take, it's going to be the coefficients are from the objective function, and the constraints, constraint constants. And then here in the dual problem, you'll have the constants, and then the coefficients from the objective function. So things are switched. And so here's the theorem. In this case, it says the objective function w of a minimization linear programming problem takes on a minimum value if and only if the objective function z of the corresponding dual maximization problem takes on a maximum value. So in other words, the maximum value of z is the same as the minimum value of w when we set it up this way. So here are the steps. 1, you find the dual standard maximization problem using the steps that we just went through. Okay, you find the you set up the augmented matrix, you transpose the augmented matrix, and then the resulting matrix is going to give you the constraints and your z function. Okay, 2, well, it's going to give you the z and the constraints for the related maximization problem. Okay, the dual. Okay, the dual problem. And then 2, you're going to solve the maximization problem using the simplex method. And then 3, the minimum value of the objective function w is the maximum value of the objective function z. Okay, now where you read the constraints and the results, okay, is going to be along the entries um, in the bottom row. So that's 4. It says the optimum solution to the minimization problem is given by the entries in the bottom row. So instead of the rightmost column, like we did before, it's now going to be the bottom row of the columns corresponding to the slack variables. Okay, not the variable columns. It's going to be the slack variables. So long as the entries in the z column is equal to 1. Again, remember, we want the z column to be equal to 1. Okay, so now before we go on to end this, to go on the non-standard, let's look at an example. Okay, so let's go here, and I want to walk through an example because I thought it'd be better just to pull up the textbook and record an example than me trying to type it all out again. Okay, give me a second here. Okay, so let me go to a problem here. Which one is this? Oh, that's right. This one here. It's the one I want to do. Okay, so here's the one we were working on. Okay, and we transposed it, and we got the associated maximization problem. Okay, and so the first thing, once you get the maximization problem, so if we go back to here, so here's the maximization problem. Oh, which one? Hold on, go back to this one. This one here. So here's the setup. This is our augmented matrix that we had. So now we're going to use these to set up our constraints, and this is where the system came from, this one right here. And so we add our slack variables, and we add our z column, and so we get 1, 2, 1, 0, 0, and then 8, and we get 5, 2, 0, 1, 0, 16, and then negative 9, negative 10. So remember, we move the two variables to the left, and they become negative, right? Just you're solving for equal to 0. So we get negative 9, negative 10, 0, 0, 1, 0. So notice that our slack variables are the basic variables in this case. And then, of course, we find the pivot. Now once we get it transformed into a maximization problem, it's the same thing that we did before. We locate the pivot column. So we find the negative the indicator that's most negative. So in this case, it's going to be 10. Okay, and then what we're going to do is to find the row, we're going to divide the constants 8 and 16 by our two coefficients in our pivot column. And so this will become 4 and this will become 8. So we choose the smallest one. Okay, remember, if these are either 0 or negative, we discard them. Okay, but in this case, we're fine. So we get 4 and 8. So this is going to be the smaller quotient. So that means 2 is our pivot, and therefore it's highlighted. Okay, now we're going to use this as our pivot to eliminate the other two entries as 0. So we go through our operations, and we change these to 0, and all these two columns or rows will change. And then we do it again. So we find the negative. This is the only one. So we find this one. This is going to be our pivot row. And then we divide 8 and 8 by 1 and 4. And of course, this is going to be our minimum value, this 2. And so 4 becomes our pivot. And so we're going to use our elementary row operations to change the other entries into 0. And so we do that, and we get this tableau. Okay. Now, there are no more negative indicators, so we're done. Okay. Now, we just make sure that everything is divided by 1. Okay. Or excuse me, that our basic variables. So what are the basic variables here? Well, our two basic variables here are x1 and x2. Okay, so now we're going to divide this row by 8 to make this one. We're going to divide this row by 4 to make this one. And when we do that, we get this final matrix. Now, since we've got 1 already here for z, we don't have to do anything. So now that we've got it in our final form, we can read across the bottom. And so that means if we take 4 times x1, right? And, excuse me, 4 times y1 and 1 times y2 will get a minimum value of 48. Notice that this column here, like we normally did, this is the results, this is the solution for the maximization problem. So notice down here for the maximization, if x1 is 3, or excuse me, x1 is 2, and x2 is 3, then we'll get a maximum value of 48. But if we're looking at the associated minimization problem, this would be associated with y1, y2, and it would have a minimum value. Okay, so that's it. That's the only thing. So again, practice this. Make sure you ask questions in class. Please email me if you get stuck in anything, and send me your work on as an attachment, and I'll be more than happy to help you through the process or to confirm that you did it correctly. So again, please make sure you watch these videos and practice all of the problems. Do the try-its yourself. There's your turn. There's some your turns in here that also are great practice problems. And if you want to know whether you did them right, just send me the work that you did, and I'll gladly take a look at it. Other than that, I'll talk to you later. You have a great day. Bye-bye.